Hey everybody, great to have you back. So we're going to get started with some practice problems here. We're just going to briefly go over some practice problems with regard to wavelength and frequency, as well as energy and frequency, and what we can determine from that as far as inverse relationships, directly proportional, inversely proportional. But what we're going to start off with here is wavelength and frequency problems, set number 1. Now, looking at this, I think I went through and I picked out probably 2 to 3 problems that I think are a pretty good example of what the math needs to be for this problem, or for this type of equation. Remember, the equation is C equals lambda times frequency, where C is the speed of light. Now, that's a constant. That is always going to be a constant. Lambda is your wavelength, kind of looks like an upside down Y, and F is your frequency. Always remember, too, that C, the speed of light, it is always 3.0 times 10 to the 8th meters per second. So let's go ahead and take a look at number 3. Going through number 3 and reading, we see that we are trying to solve for our wavelength. And we have a frequency of 460 times 10 to the 12th hertz. Not correct scientific notation, we know that, but that's okay. And remember, hertz is 1 per second, or per second. Write out our equation, C equals lambda times F, and now we start to fill in. 3.0 times 10 to the 8th meters per second equals our wavelength, what we're solving for, times our frequency, 460 times 10 to the 12th hertz, or per seconds. In order to solve for lambda, we now need to divide, forgot about this. Remember, hertz is per second. So we need to divide 460 times 10 to the 12th hertz, both sides. In doing this, we will be able to cancel out the right-hand side of the equation. Oh, we like to cancel in red. Come on, there we go, cancel in red. And now our hertz also cancels out with our seconds, and we're left with just meters. This will give us a wavelength in just meters. I'm punching through and I'm calculating this as we speak. Come on, Mr. F, a little quicker on the calculation. All right, there we go. So wavelength comes out to be 6.5 times 10 to the negative 7th meters. Now, often cases, you will have to convert those meters into nanometers, or you will get nanometers first, and then need to convert it into meters, because that equation only works when your wavelength is in meters. Well, let's just do a quick conversion just to remind ourselves how to go between meters and nanometers. We have our 6.5 times 10 to the negative 7. We know that for every 1 meter, we have 1 billion, or 10 to the 9th nanometers. Multiplying this out, this gives us 650 nanometers, which confirms is in the red light part of the continuous light spectrum, or the electromagnetic spectrum, visible portion. Continuing on, I think we jumped to question number 8 next. I think I'm just going through now and reading what question I want to do. Remember, I wrote this first, and now I'm doing this voiceover, video over. Question number 8. Hey, good job, Mr. F. So question number 8, we're going to read through, and we're going to notice that now our wavelength, we're given a wavelength, it is, drum roll please, 3.0 times 10 to the negative 7th meters. We have to calculate a frequency from here. So again, we're going to use that equation, C equals lambda times F. From there, remember, our C is a constant. It's always 3.0 times 10 to the 8th meters per second. And that's going to equal our lambda, 3.0 times 10 to the negative 7th meters, times our frequency. From here, again, we're going to divide 3.0 times 10 to the negative 7 meters. Divide that by both sides. That will then allow us to cancel out, leaving just frequency alone by itself. Where's my red cross out? Boom, boom, slash, slash, cross out those meters, leave just per seconds. And remember, per seconds is also hertz. So whenever you have a frequency, you're always dealing with the units of hertz. Continuing on, we find that our frequency will equal, I gotta get quicker with the calculator. Frequency equals 1 times 10 to the, 1.0 times 10 to the 15th hertz, or 1 over seconds. Either would be acceptable. You'll see hertz more often than you will see 1 over seconds. All right, and just as a quick review, looking through this, you have to apologize, I just had some roasted vegetables for lunch. They were quite good. So as a quick review, looking through here, when our wavelength, as wavelength increases, it's the up arrow, as wavelength goes up, the frequency will decrease. Okay, they are inversely proportional. Conversely, as wavelength or lambda decreases, the frequency will increase. It's very important to realize that these are inversely proportional. Okay, inversely proportional. Okay, now we're going to jump onto the second sheet, the spectrum calculation sheet. We're going to do a couple examples with regard to our second equation, E equals H times F, our energy equation. So here is the spectrum calculations sheet. I'm just writing out the title, obviously. Hopefully you guys enjoy these videos, kind of voice over, video over exactly what I'm writing here. First example we're going to do is we are going to do question number 2. All right, number 2. Our wavelength is given. It is 6.8 times 10 to the -7th meters. Our frequency, we don't know what it is. All right, so we're going to use C equals lambda times F again, because we're dealing with a frequency and a lambda, or a frequency and a wavelength. 3.0 times 10 to the 8th meters per second equals our wavelength, 6.8 times 10 to the -7th meters, times our frequency. I know you know what to do. We're going to divide both sides by 6.8 times 10 to the -7 meters. Doing this will allow us to cancel it out on the right-hand side, and it'll also allow us to cancel out the meters on the left-hand side, leaving us with just per seconds or hertz. This will give us a frequency of just, waiting for that calculation, Mr. F, come on. It's fun because I can criticize myself on this. Frequency equals 4.4 times 10 to the 14th hertz. Now, take a look at that. The 3.0 times 10 to the 8th, we don't care about sig figs with that. However, we do care about the sig figs with the 6.8. 2 sig figs there, so we round our answer to 2 sig figs as well. Now, the color. Now the color matches the wavelength. So this wavelength would be 680, so this would be roughly in your red. But remember, as lambda has to be in nanometers in order to determine the color. So we're going to take 6.0 times 10 to the 7th meters. We're going to convert that again to nanometers, remembering that 1 meter on the bottom is equal to a billion, or 10 to the 9th nanometers on top. This will give us 680 nanometers, which then leads us to, or confirms, the fact of a red color. Looking at our spectrum, I'll show you a spectrum a little bit later in this video, but that gives us a red color. All right, the next example we're going to look through is with regard to the second equation, E equals H times F. So that's energy equals Planck's constant. Remember from our notes, Planck's constant is a constant similar to the speed of light, meaning that it'll always be the same number. So let's just do a little quick review of that equation. C equals lambda times F. There's our new equation, E equals H times F, where E is the energy, H is Planck's constant, 6.626 times 10 to the -34th joules seconds, and F again is the frequency. All right, 3b, E equals HF, that's the equation that we're using. It's a pretty straightforward equation. It's just multiplication or division, same as the one before. Energy equals, we were given Planck's constant, it's always 6.626 times 10 to the -34th joules seconds. Very important to understand that it is joules times seconds. It is not joules divided by seconds, no way. It is not joules per seconds. It is joules times seconds. Very important to remember that. All right, getting that out of the way, we can continue to write down what our frequency is. Our frequency happens to be 7.3 times 10 to the 14th hertz, or per seconds. All we have to do is multiply this out. The hertz and the seconds cancel out, and that leaves us with just joules. Now, joules, those are the units for energy. Calculating this out, we get man, Mr. F, you got to get quicker with the calculation. Hopefully you guys are beating me to the punch here, and you guys already have your answer ready to go. So we'll get an answer of 4.8 times 10 to the negative 19th joules. Now again, joules is the unit for energy. It's spelled Joules, joules, but we pronounce it joules. Now I just want to do a little bit more of a review and link all of the energy, the frequency, and the wavelength all together. There's our visible light spectrum. We see that the spectrum extends from 400 nanometers roughly on the left-hand side, the purple, the violet side, all the way to 700 nanometers on the right-hand side, the red-orange side. Red is your largest, violet is your smallest in wavelength. I had a pretty hard time here. I constantly moved the, yep, you'll see me moving it right there. It was kind of a little bit of a pain to get it, to use this, but hey, we made it through. So on the violet side, you have your short wavelength. On the red side, you have your long wavelength. Now, please remember that the short wavelength has a higher energy, a higher frequency. So high energy and high frequency on a short wavelength, and on the long wavelength side, we have low energy and low frequency. Energies and frequency, they are directly proportional. They stick together, while the wavelength is inversely proportional to both. That's kind of like the oddball. They do the opposite. So I think I'm going to review here a little bit more, just write that out for you, and then this video will be all set, and hopefully you guys will get this. Okay, we'll zoom out a little bit there, where I think we're going to erase the top. It's all like the play-by-play. Must be what it's like to be a sportscaster. All right, we're just going to make this connection one last time here. Remember, practice, practice, practice. So the higher the wavelength, the lower the frequency, and the lower the energy. The lower the wavelength, guess it, the higher the frequency, as well as the higher the energy. Very good. And that is it, guys. I hope you've enjoyed this video. Please make sure to like and subscribe. All right, everybody, take care. Bye-bye now.